Okay, so picture this. You've spent months, maybe even years, building this absolutely brilliant AI model. It's trained, it's smart, and it is ready to go. The hard part's over, right? Well, not so fast. Today, we're going to dig into the part of the AI journey that nobody really talks about, but is incredibly difficult, getting that model out of the lab and into the real world.
And that's a question that trips up so many people. All the focus goes into the algorithms, the training, the data, but then you hit this massive wall. So what's the real final boss of machine learning?
Yep, it's putting that model to work. That last mile of AI deployment is where theory crashes into reality. And believe me, it is where things get really, really tricky. Today, we're going to tackle two of the biggest hurdles out there: the specialized hardware puzzle and the just overwhelming problem of scale. All right, so let's dig into this first challenge. See, when you train an AI model, you're teaching it. But when you deploy it, you're asking it to make predictions, right now on live data. That's a process we call inference. And to do that fast enough for the real world, think of self-driving cars, spotting a pedestrian, you can't just throw it on any old server. You need very specific, very specialized processors. So this really lays out our options, right? Your regular CPU, that's your flexible jack of all trades. Then you've got GPUs, which are absolute beasts for training models, because they can do thousands of calculations at once. But man, they suck down a ton of power. And then you have FPGAs, or field programmable gate arrays. Think of them like Legos for circuits. You can literally reprogram them to be the exact perfect chip for one specific task. That makes them incredibly efficient and fast for inference, especially on devices where every watt of power counts.
And that's the big question, isn't it? You're probably thinking, okay, if these FPGAs are so perfect, why isn't everybody and their brother using them? Well, there's one massive barrier holding them back.
And there it is. This quote just hits the nail on the head. To program an FPGA, you have to use something called a hardware description language, or HDL. This is not your friendly neighborhood Python or Java. No way. This is deep, hardcore stuff that requires you to think like a hardware engineer. And most data science teams, they just don't have that skill set. It's a huge bottleneck.
So you've got this amazing tool, but it's locked behind this crazy, complex language. What do? Well, a team of researchers came up with a pretty brilliant solution. What if you could just automate the whole darn thing?
They basically invented something called firmware as a service. And the best way to think about it is like a vending machine for hardware code. A developer walks up, puts their software model into the slot, and out pops the super complex, ready-to-run hardware code on the other side, all handled automatically by a service in the cloud. And the workflow for the developer, it's almost ridiculously simple. Step 1, you just upload your model to cloud storage. Step 2, you make one simple API call. Then the magic happens. The service does all the heavy lifting, generating all that crazy hardware code. And finally, boom, you get a unique ID to deploy it with a single click. All that complexity is just gone, hidden away.
All right, problem 1, kind of solved. That's awesome. But you know what happens when you're successful? You get new, bigger problems. What happens when it's not just one model you have to worry about, but hundreds? This brings us to our second great challenge: massive, mind-boggling scale.
Yeah, 500 plus models. Just let that number hang in the air for a second. We are so far beyond a couple of side projects here. We're talking about a whole fleet of models, each with its own versions, its own needs, its own update schedule. The complexity just explodes.
And that, my friends, is a logistical nightmare. Suddenly you're asking all these questions. How do we keep track of all the versions? How do we update things without breaking the whole system? How do we deploy them so they can actually scale? Most of the tools out there, they're built to handle one model really well, but you throw a whole fleet at them and they just fall apart. It is pure infrastructure chaos. This really is the million-dollar question for pretty much any big company using AI today. How in the world do you manage an entire fleet of 500 plus models without everything descending into total chaos? You need a system, an orchestrator. And the solution, it turns out, is to build something like an air traffic controller for your models, a central command center that can manage, update, and serve every single model from one place, making sure there are no collisions and no chaos.
And here's the tech stack they use to build this thing. First up, Kubernetes. Think of it as the operating system for your whole cloud setup. It manages all the resources. Then they brought in MLflow. That's like the central library or the card catalog for your models. It keeps track of every single model and every single version. And finally, the special sauce, a custom REST API. This acts as the single front door, one unified way to talk to any of the 500 plus models. Okay, now if you're going to build a system like this, you have to prove it actually works. And the first big test is something called strong scaling. It's a simple idea, really. It asks, if I have a set amount of work to do, like handling 1,000 requests, and I throw more computers at it, or pods in this case, does it get done faster? You're hoping for a nice, clean speed up.
And the second test is weak scaling. This asks a different but just as important question. What happens when my business grows? As more and more users show up and I add more pods to handle them, can my system keep up? Can it handle a much bigger workload without slowing down? This is all about proving you can handle growth.
And the results for strong scaling? They were pretty awesome. Check this out. When they doubled the resources from 1 to 2 pods, bam, they pretty much doubled the speed. When they jumped to 4 pods, they got a 3.5 times speed up. This is exactly what you want to see. It proves that adding more resources makes the system proportionally faster. It's efficient.
So we've looked at two really different, really difficult problems here, right? Getting onto specialized hardware and managing a massive fleet of models. But what's cool is that both solutions point to the exact same powerful idea about where all of this is heading.
And this right here is the big takeaway from all of this. The solution to all this crazy complexity isn't to add more complexity, it's abstraction. It's about building powerful tools that hide all the messy, low-level details behind simple, powerful interfaces.
And when you get abstraction right, it just unlocks so much potential. Your developers can go back to what they love, building great models, instead of learning hardware design. Your engineers can manage the whole forest, instead of getting lost in the individual trees. It basically gives everyone democratic access to these super powerful tools. And the bottom line is you can innovate way, way faster. You know, this quote from that first paper on hardware it sums up the whole philosophy perfectly. The goal is to make the entire workflow as transparent as possible for the person actually using it. Whether you're generating firmware or serving 500 models, it should feel effortless.
So it leaves us with this really exciting question, right? If we can automate and abstract away the absolute hardest parts of deployment, the hardware, the scale, what happens next? What kinds of mind-blowing AI applications are just waiting to be built now that the biggest roadblocks are finally being cleared away? That's what's truly exciting.